Professor Wolfport is a neuroscientist and a world-renowned thought leader in the fields of computational neuroscience. He specializes in sensorimotor control and learning, transforming our understanding of how the brain controls movement. His research combines theoretical studies, computational simulations, and human psychophysics to understand the basis of skilled motor behavior. He began his career as a medical doctor after completing his medical degree at Oxford, followed by a PhD in physiology from Oxford as well. He then pursued research in brain and cognitive science, neurophysiology, and motor neuroscience before taking on a co-directorship at the Institute of Movement Neuroscience at UCL. He moved to the University of Cambridge in 2005, where he was professor of engineering and a Royal Society research professor. And in 2018, he moved across the pond and joined the Zuckerman Institute Mind-Brain Behavior Institute at Columbia University as a professor of neuroscience. He is a recipient of numerous awards and accolades, including the Royal Society Francis Crick Prize Lecture in 2005, the Minerva Foundation Golden Brain Award in 2010, and the Royal Society Farrier Medal in 2020. On a personal note, I first read and learned about Daniel's work as an undergraduate student, so I'm really excited to host this talk and hear Daniel's progress. So it is now with my great pleasure to welcome Professor Daniel Wolpert to the virtual stage for his Turing Lecture on the science of movement.
Well, thank you so much, Anuj, and it's a real pleasure to be here today to talk to you, even if only virtually. So I realize that most of you probably don't care about motor control, which is fine. And I'm going to try and persuade you that it's an interesting subject from a computational point of view and behavioral. My lab sort of works on how humans control movement. We do experiments in humans. We try to build models of that learning. And over the years, we sort of focused on how does a person learn a single task. We bring them into the lab and give them a task to do and try to work out what's going on. But it's become apparent to us in recent years that actually misses a lot of the interest, that we don't just learn a single task over our lives. We're born, we have a continuous stream of sensory motor experience, and through that we learn many motor tasks and build up a sensory motor repertoire. And when we begin to think about building up that repertoire, it opens up interesting new computational questions. So, if I could illustrate this with a very British thing, making a cup of tea. As your hand moves in free space, it has different dynamics to when it's interacting with the kettle. And then again, it can be in free space again and interact with the teapot, and then back to free space and then interact with the kettle again. And we can sort of label these things as discrete changes in the properties of the arm. They're different contexts. So, we could say, these cyan ones are the context where you're handling the kettle, and these orange ones, green ones are ones where the hand is free in space. And clearly, as a motor control person, you want to change the way you control your arm under these different contexts. And more than that, there are different states of the world. So as you, in the context of holding the kettle, as you pour from the kettle, you're changing the state of the kettle. And similarly, as you switch the teapot around to warm it, you're changing the dynamics. And so fundamentally, we want to understand how does the brain break down experience and use that experience to build up a repertoire. And to take you through that, I'm going to start off with some sort of basic understanding of how we study this sort of thing in the lab. So I'm going to take you through the methodology we use, and then give you a little bit of background of the sort of experiments we do, so that you get a feel for where we're going to what I really want to talk about, which is a new model called the COIN model, which is a model of motor repertoire learning, which we're excited about. And it's exciting from us because it deals in a very nice way with when should you create a new memory, how should you express the memories you've got, and how should you update them. And I'll show you a few experimental tests of the model on new and existing data. So I need to start just talking about what sort of motor learning I'm thinking about, because there are many forms of motor learning, which I'm not going to talk about. So there's strategy learning, what is the right way to tie a shoelace? There's skill learning, how can I reduce my variability to trace something like this metal sculpture with a loop? There's sequence learning, which we all know about when you have to use a typewriter or a keyboard. There's optimization, what's the right way to generate my best serve? But what I'm really going to focus on today is adaptation. And that is, how do you learn the physical properties of the world? How do you learn the dynamics of your own arm? And how, when you interact with tools, do you internalize those dynamics so you can operate on the multiple tools that we have to operate with in daily life. And to study adaptation, what we really need to do is give people novel tasks. And so we want to give them novel dynamics to see how they learn. And by novel dynamics, I mean we're going to look at reaching movements where we focus on the arm and hand, where we're going to change the relation between the commands you generate and the consequences by applying forces to you. Now, there are many ways we could apply forces. We could, attach weights to your arm, or give you a tool to hold, or take you into space, which is zero gravity, or we could give you an interesting gyroscope to hold, or put you in a rotating room so you experience Coriolis forces. And all these have been used to study learning novel dynamics. But from our point of view, they don't give us the flexibility to really control the dynamics in a precise way. And for many of these, you may have experienced, for example, weights in your arms outside the lab. So if we bring you into the lab, we're not really looking at de novo learning. So we want to go to a lot of effort to make sure the experience we give you is something you haven't experienced outside the lab. So we can look at novel learning rather than maybe recall of something you've experienced. And to do that, we make use of robotic technology, not robots to do things in the world, but robots to perturb your movement. So the idea is you hold onto a robot, it can track your movements and perturb you in interesting computer-controlled ways. And so we can look at how you learn to interact with this novel device. So all the experiments that I talked about today use two-dimensional robots. We have three-dimensional ones as well, but I will focus on two dimensions. So here's a two-dimensional robot. It has optical encoders, so you can track the movement at high precision at 1,000 hertz. And then it has torque motors, so you can generate forces also at 1,000 hertz. And by linking the state of the robot to the forces, you can generate passive movements, you can generate physical objects, you can perturb the movement. And then we have a very poor man's virtual reality. We have a screen pointing downwards with a mirror. So you see virtual targets and feedback of your movement in the plane. And here's a typical subject in one of our apparatus. So we can ask you to hold on to the robot, which I'm not showing you here, and just move to targets. And if the robot is turned off, we call that a null field. It's like moving naturally. You're holding the robot, it's got very little passive dynamics. And I'm going to call that P0. It means there's no perturbation. Okay. But then we can apply state-dependent perturbations. And one of the perturbations we particularly like is one where the force in the X and Y direction is some gain times this matrix times the velocity of your hand in the X and Y. And if we plot out the sort of force field or the vector field of that force shown here, if you're stationary, clearly you get no force. The faster you move in any direction, the bigger the magnitude of the force. So the magnitude scales linearly with speed. And the force always acts to right angles to your current direction of motion. So if you move to the right, you'll get pushed up. If you move up, you're going to get pushed to the left. So if you were to make a movement straight ahead like this, you're going to get a force field pushing you to the left. Okay, and this is an unusual force field, and it's rather nice because you won't have experienced it outside the lab. It's an unusual force field, but it means we can look at novel learning in this sort of situation. Okay, so we can apply the force field in this direction. We're going to call that a P plus force field when it's in the counterclockwise direction. And we can change the sign of this gain here. Sorry, we can change the sign of this gain to apply a clockwise force field, P minus. So throughout this talk, I'm going to talk a lot about P0, P plus, and P minus. P0 meaning nothing, P plus meaning a field in one direction, P minus a field in the other direction. And in all our experiments, we counterbalance which direction P plus and P minus is across our subject. So you don't have to worry, they're just opposite in terms of the forces. So if we take a subject, often to make movements between targets and P0, they'll make nice straight line paths shown here. If we turn on P plus, the force field, the air will get perturbed, they'll reach the target, but with a curved movement, and they'll experience a big force on their hand. But if they keep making that movement for 20 minutes or so, they'll make nice straight line movements. Interestingly, also, they won't be aware that the robot's still perturbing, and they internalize that force field, so they're not really aware the force is there anymore. And if we suddenly turn it off, go back to P0, we see a post-exposure after effect here. So people can learn these state-dependent force fields. And one way to quantify the learning is, how far do you deviate from the straight line, the maximum perpendicular error, and that's shown here. So here's a typical learning curve in the exposure phase. We see the error reducing. Now, it turns out this measure of error is not a useful measure for us for two reasons. One is it's contaminated by things we're not interested in, like co-contraction. So one way to compensate for a force field applied to your arm is just to stiffen up your arm so it's got less kinematic effect on you. And that's not true learning. That really is sort of a non-specific learning as opposed to something really compensating in a precise way for the force field you're experiencing. And second reason is it's hard to turn this measure in centimeters, for example, into how much have you learned of the force field. So methods have been developed in the field that we use called channel trials. And the idea is occasionally, 1 out of 10 trials during this learning phase, the robot, rather than generating a force field on your arm, generates a stiff channel between where you start from and your target. So we generate a one-dimensional spring, which is stiff, which constrains you to a straight line to the target. So from the point of view of the participant, they think they're doing a great job. All of a sudden, they make a perfectly straight movement to the target. And they're really unaware that we're putting them in a channel. But what the point of this channel is that we can measure the forces they produce into the channel wall as a marker of their anticipatory expectation of the force they're going to compensate for. So for example, perhaps early in learning, they produce this force into the channel wall. And we can work out from the speed they move and the force field we would normally produce on a P+ trial, what the ideal force would be to compensate for that perturbation. And then we can quantify this adaptation. This is maybe 30% adaptation. Maybe later on they get to 50, and by the end they get to 75%. So it's a way of quantifying between 0 and 1 or 0 and 100% how much they're compensated for. And what I'm showing you here is exactly the same data here now, but it's more sparse because only 1 in 10 trials is this sort of channel trial, but this now is in units of adaptation. So they start from 0, and by the end of learning, they're at about 70% adaptation. Okay, so we're going to use this measure to quantify learning. So I'm going to take you through just a few examples of how we can use these experiments to look at how do you learn multiple things. There's been maybe 1,000 papers using these sorts of paradigms to study learning of one thing, but rather few asking how do you learn multiple. So one thing we can do is we can bring a subject in and ask them to make movements to a target under a P+ force field. And when this little green light is on here, they're going to get the P+ force field. But interleave randomly with the P+, a P- force field, where the light is now on the other side. Okay, so with the location of this sort of light being on the left or right will tell them which force field they're going to get, and we're going to randomly choose in every trial a P+ or P-. So I'm going to show you many examples. I'm going to show you pictures of these two types of trials on left and right. In reality, the actual hand is in the same position for both of those, and that's sort of important. Okay, so we're going to randomly interleave these. Cognitively, we can tell them if the light is on the left, you're going to get one force field. If it's on the right, you're going to get the other. And the way we're going to assess learning is occasionally we're going to do a channel trial. And if we plot the adaptation over the course of an hour of this experiment, there's effectively no learning at all. It's effectively impossible for you to use the static visual cue to switch between these two force fields. And even if you cognitively tell people that it's relevant, this target to the force field, they simply can't use that information to learn, which is somewhat surprising. But we can change the paradigm just a little bit. Rather than making this cue just a static visual cue, we can now make it the place the hand starts the movement. So the hand's going to either start from the left or right cue. So it's going to do a lead-in movement to this point, dwell there for some time, and then go on through either the P+ or P- force field. And critically, the direction of lead-in is going to be predictive of the force field you get. So if you lead in from the left, you're going to get the P+. If you lead in from the right, you're going to get the P-. And in different groups of subjects, we're going to ask them to wait at this via point for different amounts of time. So if you have to wait for 1 second here before you go through, there's no advantage to doing this lead-in. You see no learning at all. On the other hand, if you only have to wait for half a second at this via point, we begin to see substantial learning. And if you only have to wait for 150 milliseconds or only dwell for the briefest moment, 0 milliseconds, you see substantial learning. So it suggests to us that what you do in the last 500 milliseconds or so before you go through one of these force fields allows you to separate out different motor memories. So if you do something different in the last 500 milliseconds, you can then associate that lead in somehow to separate out your motor memories and now store P+ and P- separately and recall them appropriately. So the recent past seems to be a strong cue or contextual cue to allow you to separate memories. And so we thought if the past was important, could the future also be important? And so maybe what you're going to do in the future could allow you to separate out motor memories for these things. So we have a control group which is very similar to our lead-in group, in which subjects make a movement just to a point, just to a target, either under P plus or P minus. And there's just an irrelevant target up here, which is either on the left or the right. It's predictive of the force field they're going to get, so they could use that, but as you know, they can't use static information. But we now have another group who are told to move through the force field and either follow through to the left or follow through to the right. The follow through movement doesn't have a force field on, but the follow through they get to do is predictive of the field they're going to get before the follow through. So if they're asked to follow through to the left, they're going to get a P plus force field. They have to follow through to the right, they get a P minus force field. And when we do this experiment, we see substantial learning. So it says not only does lead to different memories, but doing different follow throughs after you do a skill can lead to having separate memories for that skill, allowing you to store P plus and P minus separately. And this is interesting to us because it's always bothered me in sports why people tell you to follow through. After all, once you've made contact with the ball or let go of a ball, it doesn't really matter what happens. There's no reason to do a consistent or a follow through. But if what I've told you is true, if when you follow through and different follow throughs lead to different memories, if you were to learn a skill with a single follow through, you'd be putting all the learning of that skill into one memory. Whereas if you did a single skill here, but did it each time with a different follow through, you might be spreading the learning over different memories. And so the idea of that what happens in the future affects the memory you're going to store that skill in could explain why you want to do a consistent follow through to speed up learning. So we did exactly this experiment. One group of subjects did a P plus field followed by consistent follow through always to this target. Another did P plus to here followed by a variable follow through each time they were asked to follow through to a different target. So here it's just learning a very simple single skill. And what we found is the group who did the consistent follow through learned significantly faster. And modeling on this suggested that there was effectively less forgetting between trials in the consistent follow through as though they were putting it into one memory rather than switching between memories. Now, I don't want to claim this is the only reason that people follow through. It's just one possible reason you might want to follow through is to put all that learning of your golf swing into a single memory rather than spreading it out. But it's interesting to ask, what is it about the follow through which allows you to basically separate out those memories? And this is actually just a replication. So there's two new groups, a group who don't follow through and they can't learn based on a static queue, a group who do follow through again and can show significant learning. But we can ask, is it just the execution of the follow through which is critical? So we have a group of subjects who start off with no follow through targets. They start off the movement and they experience either the P plus or the P minus force field randomly. But halfway through the movement, we turn on the follow through target appropriately. So if they were in the P plus force field, they get the left follow through target. In the P minus, they get the right one. And then they're asked to follow through. So they could learn to associate that target they followed through to with the force field they experience. And the way we test that is on some trials, we turn on the follow through target from the beginning and we measure the force they produce in the channel. Of course, there's nothing to learn now because they're in the channel, but we can assess adaptation. And the answer is the execution group here in yellow show no learning at all. So just executing a follow through doesn't help you separate out the motor memories. Now we can have another group who get to plan a follow through, but they never get to execute the follow through when they experience the force field. And the way this works is the follow through target is on from the beginning. They start going through in the appropriate force field. If the follow through target is on the left, they get P plus. If it's on the right, they get the P minus. But halfway through the movement, we turn off the follow through target and they have to abort their movement here on the green target. So they never get to make the follow through. Now you might think, why on earth would they bother to plan it if they never get to make the follow through? Well, the reason is we put many of these trials in where the follow through target is on throughout. So they start planning it, but they're in a channel, so there's nothing to learn. So anytime they experience the force field, they don't follow through, and we can assess adaptation on these follow through trials. And what we find in this group, shown here in red, is they learn just as well as if they did a true follow through. Suggesting the critical thing for separating out memories is not the physical state of the arm, it's the mental state you create by planning a follow through movement. And I don't want to go into the neurophysiology of this, but the idea is you put your brain into a different neural state by planning a follow through to the left and the right, which allows you then to associate the different neural states with different force fields. So the recent past and the future determine the current motor memory, and planning actually is more important than execution. So if you want to be able to learn multiple things, planning different things after you do them is actually a good way to do it. Now, I don't want to make you feel that the only way you can learn multiple things through follow through and lead in. It's just two contextual things we've been interested in. But we're also interested in tool use. And if you look at these birds here, each of them has generated a beautiful single tool for their ecological niche. But humans are amazing at stealing and using all of these tools. So we are masters of the ability to use multiple tools in many different ways. And one thing we can ask is, when you learn a tool, such as a cup, do you learn it in a holistic manner? Do you learn it as a physicist would learn it? F equals ma, and that's the properties of a cup. Because in fact, the way we interact with cups is very control point dependent. And by that I mean, depending on what I'm doing, I want to control different points in the tool. So when I want to drink from this cup, what's important is the compliant interaction between the hard lip of the cup and my soft lip of my lips. But when I want to put the cup down on the table, what's important is the sort of hard frictional properties between the base of the cup and the table. And those have very different dynamics. Now, you could learn the whole thing as a single entity, or you could learn the physics of a cup in a task and control point dependent manner. And so one question we want to ask is, when you operate on a tool, do you break that tool up into the relevant points you want to control and associate each with maybe different dynamics? And to do that, we're going to have subjects move with a virtual tool. Here is our virtual tool. It's a little virtual rectangle, and you can see its reflection in the mirror. This is what the subject actually sees. They see their hand, they see the robot handle here, and as they move, this object translates for them. So the tool moves with them. And there are different points on the tool, and we're going to ask them in different trials to control the different points to do the task. So here's our critical test group. They hold the tool, and we say, when the left target comes on here, move the left control point to that target. When the right control point, when the right target comes on here, move the right control point to the target. Now, you'll notice that where we set things up, this movement for these two trials is identical. It's just a straight ahead movement. But the only difference is they're being asked in one to move the left control point to the target, the other the right control point to the target. And then what we do is we apply a P- force field when they're controlling the left control point, a P+ when they're controlling the right. So effectively, the movement's always identical. The only thing which tells them whether they're doing P- or P+ is which control point they're producing. And we contrast this group with the control point group who do a single control point. Again, now we have these targets on the left and right, but they're irrelevant to the subject. They're told now always move the central control point to the target. So this group makes identical movements and gets identical experience in terms of force field as this group. The only difference is this group are told to control different control points to different force fields. And what we find in these groups is that the single control point group can't learn anything at all. But the other group who are making identical movements, identical experience, shows significant and substantial learning. So they're able to associate these different points in the tool with different dynamics. And I won't go into the generalization, but we show it really is the control points by doing different generalization. And it's got nothing to do with eye movements. They can either fixate or have free gaze. That doesn't matter. So it suggests actually when we're learning tools, we may be not learning them as holistic things, but learning them as different properties, that the control points in an object can be associated with different dynamics, even for the same movements. And that's going to be important later on. It's going to be a sensory cue we're going to exploit to test our model. Okay, so now I want to get on to what I really want to talk about, and that's a model which really comes up from the ideas I've talked about, and a model of repertoire learning. The idea is we have to handle many different objects in many different situations throughout life. And what we really get is this continuous stream of sensorimotor experience, and it may be beneficial to break down that experience into different memories. And then we have to think about how we actually create memories, how we update memories, and how we express them. And I'm going to have a few disclaimers. It's a simple model. It's a simplified abstract model of motor adaptation in the sense that we're going to have scalar states, scalar observations, and scalar action variables. It's not because we can't get more complicated, we just don't need to for the moment. It's a trial level model, so we're going to model a trial by trial learning. But I hope that even though it's going to be simple, the core computational ideas embodied in it are applicable to more complex models of motor learning. And I have to say that this model was 99% or more done by James Heald, a very talented PhD student and postdoc, and Mattia Lengel and myself went along for the ride on this model, which was very exciting. And we call it the COIN model. The COIN stands for Contextual Inference. It basically is going to put contextual inference at the core of a lot of motor learning. And we like COIN because it's a probabilistic model. So it's a fully Bayesian model, and I'm going to go through the generative model first, and then what the priors are, and then what inference is, and then a toy example before I go on to showing how it applies to data. And so the idea of this model is at any point in time, you're in one of a discrete number of contexts, an infinite number of possible contexts. So you're in the blue context of this trial, blue context again, then red, then orange. So you can think of this maybe as the kettle, free space, so, teapot, if you want. Okay, so the context can change discretely as a Markovian process. And then context can emit sensory cues. So you can see attributes which have nothing to do with motor control or your actions, things like the visual appearance. So maybe you have the visual appearance of a cup or a sugar bowl. And so probabilistically, these contexts emit sensory cues, which can be informative onto the context. Critically, each context is associated with a state. So for example, here is the state of the blue context. So you could think of this as the weight of the kettle, and this can evolve, in our case, the linear dynamical system across time. And here's the state maybe of the hand, which might fatigue, and so here is the state, again, of time of the red context, and here's the orange context. And each of these is another dynamic system which can have different properties, okay? And so these evolve whether you experience the context or not, they just evolve over time. Crucially, what you experience when you move is state feedback. And the state feedback is determined by which is the active context and its state. So effectively, we're going to assume you experience the state of the active context with noise. So over here, when the red context is active, you don't experience the blue state, you only experience the red state. Okay. And so the problem here of our motor learning is to do online recursive inference of everything you want to know. So the only things you get to experience are these observations. You get sensory cues and state feedback, and you get a stream of those, and you want to infer everything about the upper levels here, and that's a hard problem. So just to be specific, there are variables and parameters in this model. Variables are things we expect to change in our generative model. Parameters, which are things which are fixed in our model, but will change in our heads because we're doing inference, and so we'll be updating them. So the variables which we want to estimate are what's the current context. And because it's probabilistic, what we're really going to do is estimate the probability of all the contexts we've experienced so far. So the probability distribution over context at the moment. And we also want to estimate the current state of each context. We want to track the most likely state of each of our contexts. Then there are parameters we want to know. That is, how many contexts have we experienced so far? Or how many are there? What are the context transition probabilities? What are the Q emission probabilities? And what are the state transition dynamics for each context? So we need to learn all those things. To make this a tractable problem, we're going to put priors over everything we care about, and we're going to choose relatively flexible priors. So I'm going to just briefly tell you what those are. First of all, we have a prior over our transition matrix here. And so the way we do that is we have a sticky hierarchical Dirichlet prior. So it's got three hyperparameters. And the nice features of it from our point of view, and rather novel to the motor control field, is it's a non-parametric model. So effectively, there are infinite number of possible contexts, and basically the number of contexts you infer will grow in a sensible way with time, in a way which can be controlled by this prior. The hierarchical nature is also important because it actually means you can generalize from experience in one context to experience in another. So the way that we generate this is the first thing we do is we do through a stick breaking algorithm, we basically get global probabilities. So this shows you the global probabilities of how frequent is the blue context, the red context, and so on. And that's governed by one parameter. And from that, then we generate transition probabilities, basically an infinite matrix of transitions or from and to contexts, which obey this global probability, but allow fluctuations around it. Okay. And the final thing we add is the stickiness, such that generally, if you're in one context, you just stay in that context for a certain amount of time. Okay. And so this is quite a flexible, nice prior to have over contact positions, and we use a very similar ones for Q emissions. The only thing we don't have is stickiness here. But again, we have a global Q probability such that, for example, maybe cups are more common in your world than sugar bowls. And then we have effectively context can emit Qs. So for example, this particular context is most often associated with a cup and less associated, for example, with a sugar bowl. We need to specify the prior over these linear dynamic systems. We choose a very simple state transition so that the state at the next time step decays away from the previous one, and that's very classical in state space models of motor control. It can have a drift parameter as well, which is specific to that context, and then it has noise. And effectively, we put Gaussian priors over those, a truncated Gaussian over the retention, and a Gaussian over the drift. And in fact, the drift is what allows us to have long-term memory. If you have drift and retention, even if you don't observe something for a while, it will have a non-zero asymptote, which is basically a form of long-term memory in this model. And finally, what you get to experience in terms of state feedback is effectively the state of the active context plus noise. Okay, so depending on the experiment we're going to talk about, if we have an experiment which has no sensory cues, we have 7 parameters to fit. If we have a model which does have sort of sensory cues, then we have 8 parameters to fit. And so it's actually a very flexible model with not too many parameters. Okay, so the critical thing is to do online recursive inference, and actually we're going to use particle learning to do that, but let me just give you a feel for how it works. So the idea is at any point in time, you've got an estimate of your context from a previous trial, and you're going to generate a predicted probabilities of each context given what you had from the previous trial and the current sensory cue. So before you generate a movement, you may see an object in your hand, and that's informative as to what the predicted probabilities are of your context. You represent the state of each context you've instantiated. So at this point in time, you've only got a blue context, and you always maintain a distribution over a novel context. And so the right thing to do then is, given this distribution, is we weight the outputs of these to the motor output, effectively using this predicted probabilities. And this happens at the start of the movement, but once you've generated the motor command, you then get state feedback, and you can basically update your belief over context to posteriors or responsibilities, we call them. So this effectively uses your predictions here, the state feedback, and the states you've instantiated to work out the probability of the context given both the sensory cue and state feedback. And that's used to determine whether you should generate a new memory. So for example, if the novel context responsibility is high, you may spawn off a new memory shown here in red and basically instantiate a new memory. So this deals very naturally with memory creation. Finally, we need to update all the memories we have, and the way you do that again is to use these responsibilities in your errors to modulate the updating of all the memories you have to do memory updating. So let me take you through a toy example of how this actually works. So here is a toy example of experiencing, for example, a set of cups in a sugar bowl. So this is the state feedback in one dimension, the sensed weight. You start with cup 1, you go to cup 2, which is heavier, back to cup 1. You go to cup 3, which is heaviest of all, and maybe you empty that of water and back to cup 1. And all the time, the sensory cue is constant. They're all identical cups, so they all look the same. I then go to the sugar bowl, which has got a different sensory cue. And in this case, the sugar bowl happens to weigh the same as cup 2, okay? So the input to the model is going to be the sensory cue, which in our case is a discrete index, and the state feedback, which is not this beautiful black line. It's going to be a noisy version of that shown here. Okay, so you get noisy state feedback and you get sensory cues, and then we run our inference algorithm to do all the inference we want. And the first thing that the model works out is the probability that the novel context is responsible. So this is a rather broad prior. It's actually in the stationary distribution given the prior, and therefore we can ask how probable is this responsible compared to all the others, and that's shown here. So to start off with, because you've got no memories, it's the most responsible because it's the only one there is, and therefore you generate a blue memory. When you come to the red cup, again, you generate a new memory because the novel context has high responsibility. But note when you go to cup 2, although it raises a bit the novel context probability, it's not enough to instantiate a new memory. And finally, when you go to the sugar bowl, even though it weighed the same as cup 2, because the sensory cue for these parameter settings happens to be enough to generate a new memory. So in this case, you generate a memory, 3 memories over the course of the experiment, one appropriate for cup 1 and cup 2, one for cup 3, and one for the sugar bowl. So each time you create a memory, you have to also represent its state. And so what I'm showing you here is not just a point estimate. This is the full distribution of state for each context instantiated. So the gray in the background is the distribution for a novel context. The blue here is the instantiated context. So we instantiated context, and it tracks reasonably well the weight of cup 1. When you go to cup 2, because you don't generate a new memory, you have to adapt the state of this blue context to match cup 2, and similarly when you go back to cup 1. But when you go to cup 3, because you're generating a new memory, you instantiate a new memory here as a state, and effectively you represent that, and you still represent the blue, and finally, in the end, you have an orange, a red, and a blue context. So this is the full distribution, but we need to determine how much to express these memories in terms of our motor output. And if you remember, the way we express them is based on the predicted probabilities based on the sensory cue before you start your movement, and that's shown here. So to start off with, you've only really got the blue context, you express it fully. But when you go to the cup 3, you see that you slowly increase your expression of the context for the red and decrease your expression for the blue. And so in the model, the right thing to do is to multiply these distributions by these weightings to get the posterior over the mean state shown here in mauve. And we take the average of that, the mean, to be the motor output. So you can see here there's some interesting features. One feature which is interesting to us is here. If you saw this learning curve in the experiment, you would say the participant is slowly learning the properties of this cup. But actually, that's not the case. What's really happening in this case is that the predicted probability is slowly increasing. The actual learning of the state is really rapid. They've represented the correct state of cup 3. What makes this a slow learning curve is the fact that they're only slowly expressing. So we can call this apparent learning. This slow learning isn't true learning because you've actually in your brain got a good representation of the weight of cup 3. It's apparent learning because this curve is driven by a mixing of what you've got in your head, basically the way you express learning. And we can contrast that to what happens at this point in time when you adapt here. This is true learning because this is a real change in state which matches your expression in the real world. And I'll come back to that as an important point, that most models of motor learning don't separate out proper learning, which is a change in the state you have in your head, and apparent learning, which is a change in the expression of what you've got in your head. And I'm going to try and convince you by the end of this talk that many features of motor learning are actually apparent learning and not proper learning. Finally, after you've moved, you get state feedback. You can recalculate now your responsibilities, your posterior is shown here, and you're going to use these to update memory. So when the posterior is high here in red, it'll faithfully track the state feedback. However, when you have a low responsibility red here, it'll diffuse out as you're not observing that state. So this model does very nicely with memory creation, memory expression, and memory updating. So just to really drive home the point about proper and apparent learning, here are 3 simulations of the coin model and 3 adaptation curves. So the perturbation is shown in black here, and blue is the behavioral output. And if I said to you, which of these is proper learning, there's no way you could tell because they're absolutely identical in terms of behavioral output. But if I show you what's going on under the hood, in this case, there's one memory and you adapt that memory as a function of time. So this is proper learning. Okay, so you're basically expressing the memory always fully and it adapts as a function of time. In this case, it just so happened you came to the experiment with 2 memories, one for 1 and one for 0. And these don't change at all through this learning. But what's changing here is how much you express each. So this curve is purely apparent learning. There's no change in your brain as the representation of the states. You're just the way you're expressing them. And what we expect to happen in many situations, it's going to be a mixture of proper and apparent learning. So here's a mixture because you generate a new memory which slowly adapts its state. So that's the proper learning, but also you change your mixing, which is the apparent learning. And so now, given this model, we have a way to at least think about to what extent is expression of skills in the world a recall and mixing versus proper learning. Okay, so the learning curves I talked about earlier, where you learn a single force field, aren't rich enough to differentiate between the models we want. So we're going to have to go to some more complicated paradigms. And I'm going to describe to you here a paradigm called spontaneous recovery. It's something which has been known in sort of conditioning literature for a long time, but only came to the motor control literature in around 2006. And what you do to a participant, you bring them in, you give them a bunch of trials with no perturbation. Then you give them some P+ to learn the P+, that's the force field acting in one direction. You then give them brief exposure to the opposite force, or P-. And the aim of this is to bring behavior or motor output back down to 0. Okay, that's the aim of this. And then you're going to put them into a long series of channel trials where they're constrained to a channel trial, and you can measure the expression of learning during this phase here. Okay, so here is some data from this paradigm. Okay, I'm only showing you the channel trials here. So most of the trials are not channel trials, they're perturbation trials. So we can only plot adaptation on channel trials. So to start off with, they start off with no adaptation. Through the P+, they get to a high adaptation. When we de-adapt them, we don't have any channel trials in this phase, so that's where there's no data. But by the end of it, this particular group of subjects were at the negative, so they're expressing sort of a negative memory. And when they go into the channel trials, what you see is a spontaneous recovery. They spontaneously re-express the P+ adaptation. Okay, which is surprising. You might think they would just decay away to 0, or if we got them exactly to 0 here, they would just stay at 0. They don't. They re-express the P+. Okay, so this is a spontaneous re-expression of a previous experienced memory. And the way this has been explained in the literature till now is with something which is called a dual rate model. The idea that learning isn't just a single process. Maybe you've got 2 learning processes with different temporal properties. So the idea is you're trying to learn this force field, and the output of your learner is a combination of what a slow learner and a fast learner has learned. And what the slow learner does is it decays away slowly. So whatever it learns, it maintains, but it also learns slowly. So here's the sort of error between what I'm producing and the motor output. So it decays slowly and it learns slowly. Now the fast process, on the other hand, learns quickly, decays away quickly, but learns quickly. So they compete to learn it. They're competing to learn it and to partition learning up. So here's the output of the dual rate model fit to this sort of data. It learns the perturbation, it de-adapts, and when you go into the channel trial, it effectively re-expresses the P+. And the reason it does that is we look at the components of the fast and slow process. The fast process learns quickly, but then begins to decay away as the slow learner learns. And the blue curve here is the sum of the red and the green. When we come to de-adapt at this point here with the P-, it's the fast learner that does the de-adaptation. So at this point, when you've got no motor output, actually the slow learner is positive and the fast learner is negative, and they sum to 0. When you get into the channel trial phase, there's no error anymore at this point. So all you get is decay, okay, of learning. And because the slow decays slowly and the fast decays quickly, it reveals the slow learner. So the idea here is that effectively, everything here is driven by true learning, and the extent that in the dual rate model, there's no concept of changing expression of learning. Both the fast and slow learner can combine always to produce the output. So we can compare that explanation to what we get when we run this paradigm through the coin model. So here's the coin model. Here's the data we're going to put into the coin model, the blue dots. There are no sensory cues in this, so it's relatively straightforward. Here's what happens to the states. You start off with 1 memory for the P0. When you experience P+, you generate a new memory for P+. And when you get a P-, you experience a 3rd memory for P-. So by the time you go into the channel trial phase, you have 3 memories represented. Here are the predicted probabilities over the course of the experiment. And what's interesting is when you go into the channel trial phase, you see that the predicted probability for the red context for P+ increases over time. And the reason is the coin model has learned that P+ is the most common context. Okay, so in the absence of any information, it thinks it's the most likely one for you to transition to. And so effectively, by mixing these with this, we get robust spontaneous recovery. So here, spontaneous recovery is caused not by having fast and slow processes compete. It's really the coin model says you're getting a change in motor output without any real changes in the motor states during this phase. It's apparent learning. The dual rate model says you could only get changes in motor output by changing the states, and therefore it has to be driven by proper learning. So we can test this by making the experiment slightly different. In the coin model, if we give strong evidence that P+ is returned, it should really lead to a rapid rise in apparent learning. So what we do is we change this paradigm only slightly by giving 2 P+ trials at the beginning of the channel trial phase. And that's very strong evidence for the coin model that the P+ has returned. And so rather than seeing the slow increase in predicted probability, you see a very rapid increase in the predicted probability. And that leads to a qualitative different behavior. Rather than a slow rise, we get a rapid rise and decay, what we call a vote recovery. In contrast, we're going to see the dual rate model can't do very much for 2 P+ trials. It's not enough to change the states enough to get this sort of behavior. And so the coin model should allow us to do this. So here are 2 groups of subjects, one run on the spontaneous recovery paradigm, one run on the vote recovery, where all we increase is 2 P+ trials here, just 2 trials with P+. If we fit the dual rate model, standard model in the field does a reasonably good job on spontaneous recovery, but it really fails to qualitatively on a vote recovery. And the reason is, in order to get from here to here, it needs to have a very fast process which forgets quickly. But therefore, the fast process comes up here will forget very quickly during this phase. So it just simply can't account for the data. In contrast, the coin model can explain both spontaneous and a vote recovery rather nicely. And if we do group level BICS, it's very strongly supportive. So it suggests that context estimation may well control memory creation in this task and expression, and explain spontaneous and vote recovery in a unified way. So that's 2 elements of the model, memory expression and creation. The third element is memory updating. And I'm going to describe an experiment to test this memory updating. And this is actually this is the hardest experiment to understand. I'll do my best. In single context models, or typical models in learning, effectively you have some estimate and you update your estimate based on some Kalman gain and error. So that's typical in a single state space model. But when we come to something like this, which is really a switching state space model, now there's an extra component. Yes, you update with the error of the jth context, dependent on the Kalman gate of the jth context, but now you also update based on the responsibility that you believe that context was controlling the movement. Okay, and what this really predicts is that all memories you have should be updated proportional to responsibility. You shouldn't just be updating one motor memory. You should update all of them in a differential way. And that's an interesting prediction because many models of motor control, even modular ones, suggest you just update the most probable memory. And so we want to ask the question, can you update multiple memories at a time? Now, it might be in the real world, contexts are so all or nothing that effectively you only update one in general. So we're going to create a situation where we can control this responsibility to be intermediate and look at single memory updating under different situations. Okay, so the test is all memory should be updated proportional to responsibility. And here's the experiment. We want to engender in someone's brain 2 contexts. We want to give them really good training on 2 contexts, and we want them to associate those contexts with both the sensory cue and state feedback. And the way we do that is we're going to apply a P+ force field on them with a sensory cue 1. And the actual cues we use here are the control points I'm talking about, the left and right control point. So they see an object, they control the left control point for the positive force field, and then they control the other control point for the negative force field. And we randomly interleave hundreds of these trials. So hopefully over the course of experience, in the coin model, they've learned 2 contexts. One is associated sensory Q1 and the positive force field, and one sensory Q2 and the negative force field. And having learned that, we then want to test memory updating. And the way we do that is we wash out learning a bit with some null force fields just to get people not to be saturated at full learning. And then we're going to ask how much do they learn based on a single exposure trial. And the exposure trials we're going to use is either one which they've experienced before, P1 plus or P2 minus, things they've experienced during training. Or we're going to give them a conflict where we give them sensory Q2, but P plus, or sensory Q1 and P minus. And we're going to ask how much do they learn for the single exposure trial. And the way we're going to do that is we're going to bracket that exposure trial with a channel trial on each side, where the channel trial gives them a sensory Q1. So in this channel trial, what we're probing is what is in their brain for context 1. What's the state of context 1? Because when they see this Q1, they should express predominantly context 1. So we look at the behavior before, we give them one trial here, look at the behavior afterwards, and the difference in that is single trial learning, how much they're updating the memory for context 1 based on these different exposure trials. So let me explain the predictions. Before they move, the only thing they get to see is the cue, whether it's the left or right control point. So before they move, they should have a high belief they're in context 1 if they see sensory Q1. So this is their predictor probability. So if they see Q1 in this column and this column, they should have a high belief based on the cue that they're in that context. And if they see sensory Q2, they should have a low belief that they're going to be in context 1. However, when they move, they get state feedback of the force field, and that gives them a likelihood. And if they experience the positive force field, then they should basically have a high likelihood that they were in context 1. If they experience the negative force field, they should have a low likelihood. So as a good Bayesian, they should work out when they come to calculate the responsibility, they should mix the prime likelihood and get this graded belief that they're in the in the context 1. And this is what should drive single trial learning. The more I believe I'm in context 1, the more I should learn in general. Okay. And when we look at the behavior participants actually perform, it's shown here. It matches very nicely. So this really suggests that participants are updating all memories. In this case, they have 2 memories, but only probing context 1, but by symmetry of the experiment, we could have probed context 2 and we'd get the converse. They must be updating multiple memories and updating them in proportion to the responsibility. And that's important for models of motor learning, which have assumed you only update 1 memory at a time. We need to understand that you update all memories in proportion to the responsibility. Now, up to now, I've effectively fit 40 subjects' data individually to get these predictions. So we fit individual participants in our lab. I'm now going to freeze those parameters and make parameter-free predictions on classical paradigms of literature. So we've got 40 parameters. We don't do any fitting now. We're just going to simulate classical paradigms. And one classical paradigm is savings. Savings says, if you learn a motor task once, you go away and you come back to the same motor task, you'll learn it quicker the next time. So, once you learn a task once, you're quicker to learn it the second time. And here's a recent example. You learn a P+, it's actually a spontaneous recovery paradigm, and then you repeat it again afterwards. And if you look at the learning in the green phase and learning in the pink phase, you learn it quicker in the pink the second time. Okay. And this is often taken as that maybe you increase the learning rate or you're updating your belief about states more. But when we look at what the coin model does, it reproduces this behavior very nicely. But when we look at the critical measures of learning rate and internal representation of state, they're identical for the first and second experience. So here's the Kalman gain, which is basically the learning rate. Here's the state of which updates at the same rate. The critical thing that differs is contextual inference. That actually, having experienced P+ once, you're more willing to believe you're going from the P0 to the P+ state the second time, and that's shown here. So in fact, what's driving this is apparent learning. It's changes in the way you express your learning, not in the learning itself underlying this. The same argument applies to anterograde inference. And anterograde inference says the longer I learn one thing, the harder it is to learn something else. So if I learn P+ here for different amounts of time before I go to P-, the longer I learn P+, the harder it is to learn P-. And that's shown here. These are the curves. These are the curves spread out from the least amount, the most amount of P+ to the least amount of P+. Our model reproduces this behavior. And again, the Kalman gains and the change in the states are identical. What changes is the longer I experience P+, the less I believe I will go to a different context, and the less I'll express my P- learning, even though my P- learning is just as quick in terms of the state representation, but it's the expression that changes over time. And finally, people have been very interested in volatility and how it affects learning rates. So here's an example of an experiment published in Science a few years ago, which looked at putting participants either in a very low volatile situation, so it flips between P+ and P- very irregularly, or very rapidly. And so having experienced in different environments and different groups of subjects, they measured across time how single trial learning to these forces changed. And what they found is if you were in a stable environment, it looked like single trial learning increased. If you were in a very volatile environment, it decreased. And they interpreted this as you're increasing or decreasing your learning rate to match the environment. When we apply the coin model for that, we get qualitatively the same behavior, but critically, there's no change in learning rate. There's no change in actually what's going on in the internal state. It's all driven by contextual inference. The idea is that when you measure single trial learning on this, you give a single trial. If you're in this condition, what you experience on a single trial is likely to hang around because of the consistency, and therefore you should express it more in the next trial. So this curve here we think is driven by the fact you're willing to express it. When you do single trial learning here, because you think the field can switch, you're going to express it less. So effectively, this is the predicted probability that the field you've experienced will stay around for the next trial. And that, we think, explains this. So all these things which have been interpreted as changing in learning rates or internal states are all driven by contextual inference. I don't have time to go through it. In the paper, we go through in detail, but there are a bunch of single context and multiple context models already out there. We've explained many of these things. I haven't talked about this, but we also look at cognitive aspects to the extent which we explain explicit and implicit differences. The coin can explain all these in a unified manner. Previous models each lacked different things. Some didn't model state dynamics, some didn't model context transitions or had no centric cues, or they weren't hierarchical, or they assumed none of contexts were known. Or in the inference process, they only update or express a single memory, or they learn no or few parameters. So we think the coin model really is a key computation, that contextual inference is a key computation in this and more generally in learning of anything. It's principled because it's Bayesian. It's comprehensive because it deals with all sorts of information the brain has access to. Of course, we can make the model arbitrarily more complex, but at the moment, even in the simple form, it can explain a huge amount of data. It unifies disparate data sets. I've only shown you some of the data sets. In the paper, we went to a lot of other data sets to model to show how different features of spontaneous recovery change under different paradigms. And I think critically, it makes it very clear that there's a distinction between apparent and proper learning, which has really been sort of ignored, at least in the motor control field, and will be important when we want to go to like neural basis of behavior, that we shouldn't always think of all learning curves as representing true learning. I really want to thank James Heald, who really was a pioneer in this work, and my other collaborators and my funders. And thank you all so much for listening. I'm happy to take your questions.
Thank you, Daniel. That was a very fascinating talk. Let's hand over to our audience now and hear from them. In case anyone missed the introduction, a quick reminder about the Q&A. Please submit questions using the Q&A function on Zoom and not the chat. And let us know if you'd like to briefly join the panel and ask your question live. Just make a note at the end of your question by writing live if you want to ask with your video on. Otherwise, I will direct the questions to Daniel. We have quite a bit of questions, so let's jump straight into it. And I'm going to quickly start off. So Daniel, have you thought about how the coin model maps onto the cerebellum basal ganglia interactions? And have you thought about experimentally manipulating in a temporally specific manner some of these neural areas and how that affects apparent and proper learning? Or is that something to
that's a good question. So we're definitely very interested in that. So from the literature already, there's some evidence that things like prefrontal cortex may be responsible for maintaining context estimates. And so we know one thing from the literature that working memory tasks, for example, changes spontaneous recovery into evoked recovery. And that's actually something we model in our paper. So the idea is that maybe contexts are done in prefrontal cortex. Now, in terms of maintaining states and that we don't know. We are doing experiments. I'm collaborating with Mark Churchland's group, where we're having monkeys doing tracking tasks, where we can either change the gain of the task a little, which we think would be true learning, or we can flip the gain when they're doing tracking, which is really like a new context. And what we're finding at the moment in motor cortex is when you change the gain by a bit, the cortex doesn't care. It just produces, as long as it's producing the same force, you get the same activity in motor cortex. But when you flip the gain, even if it's producing the same force, you see dramatically different activity in motor cortex, as though it regards that as a completely different context. And so it's an open question for us as to where the context estimation is going on, what represents the state, what does the mixing. We are planning to do experiments in mice to address this as well, where we can actually record from basal ganglia and cerebellum, and we're really interested. You know, the prediction should be something needs to switch you between, it does the apparent learning, something needs to do the real learning, but we're too early a stage at this moment.
Thank you for that. From one of our participants, how does apparent and proper learning relate to explicit and implicit motor learning?
So I think we have a model of explicit implicit learning. So people have looked at particularly visual motor rotations, and maybe I can even show you here. So people do things like, this is a nice experiment where you ask people to reach to a target under visual motor rotation, and you say, where are you going to point? And people will say, I'm aiming for 4, and then they actually reach and they go to 7. So then you can quantify, this is the implicit learning, and this is the explicit. And so people look at the overall learning being a component of this explicit component, which changes over time, and implicit. And without getting too much detail, the way we think about this is when people have often tried to think of this as a fast and slow learner. We don't think of it that way. We think that what's actually happening in these sorts of tasks is the brain's got a credit assignment problem. That when you change the relationship between what the hand does and where you see it, you now have a bias between where your arm is and the feedback, which you have to learn. And our hypothesis is that now when you get an error, you have to decide, what is my bias and what's the perturbation? And we think the bias is implicit and the perturbation is explicit. And using that, without going through the next few slides, we can explain those complex time courses of implicit and explicit. So we basically think you're explicitly aware of the most probable perturbation, but you're implicitly not aware of things like your biases and your action. So we don't think they naturally map on necessarily to proper and apparent learning, which is an interesting question. And at the moment, we don't really know how much in real world learning is proper and apparent. That's still an open question. But we think we can explain at least implicit in these sorts of tasks that effectively you're not aware of your bias. Doesn't that make sense? You know, I got a proprioceptive feel on my arm. I see my arm. I don't feel there's a mismatch. I've learned that. I'm not aware of it. And again, we think that you have to credit assign between perturbation and biases.
Perfect. Before we move on to our live question, one of our participants was wondering, are there techniques other than reaching that we can use to study novel adaptation?
Yes, I mean, absolutely. So, I mean, people use all sorts. So you can use walking. So there's a nice things where you do walking on a treadmill. So you put people on the split bread treadmill and you make one belt go faster than the other, and you get beautiful adaptation of gait so that people now have a symmetric gait. So people are not a lot of work in gait adaptation. You can do eye movement adaptation. So a typical one is saccadic adaptation. So you make an eye movement to a target, and as you're making the eye movement where you can't see anything, they jump the target. So now your gain is wrong, and you see gain adaptation. So almost all motor systems show adaptation. Speech as well. If you play your speech back and change the formant to make them higher, people will adapt their speech to bring the sound they hear back to what they want. So it's all those systems. We focus on the arm just because it's a really easy experimental system to perturb. So speech is a little bit harder to perturb. Walking, again, it's a little bit harder. There's limited things you can do. Whereas with these force fields, you can produce arbitrarily complicated or simple things, which we think is a nice, tractable
right. And related to that question, like how many trials do people need on average for adaptation?
So to learn a simple force field, like one force field, they probably can learn that in, 100 trials reasonably well. Okay. When you're doing these switching ones where you're learning 2 force fields, it can take hundreds of trials. Okay. We did an experiment where the force field depended on both the lead-in and the follow-through. So basically it was an XOR. So you had 2 different leads-in, 2 different follow-throughs, and the field you got in the middle was an exclusive OR over the lead-in and follow-through. So you couldn't predict it based on the lead-in or the follow-through. And over 5 days of an hour a day, they only got to 50% adaptation. So, as we move to things more golf-like, where the lead and follow-through just, determines the force, you basically see learning stretching out in time. So these things can be very fast for simple things, but very slow for hard things. These sorts of tasks.
Right.
We like things to be on the course of an hour because we don't like doing experiments which take multiple days. So we try to titrate the force field to make it learnable in an hour.
Right. Nice. I'd like to invite one of the participants live. Sure. They'd like to ask a question on, do your models relate to modified weak fusion?
Oh, good. I'm glad they're coming on. Since I don't know what that is, they're going to have to tell me first.
I just got a note that we might not be able to host a live question. So
unfortunately, I don't know what modified weak fusion is, so I can't tell you how it relates.
Okay. No worries.
Ugin, do you know what modified weak fusion is?
No, I don't either.
Okay. Well, if you tell me what it is, I don't. Yeah, sorry.
And that's okay. The last question is, when you talk about planning and follow through, is that an explicit decision or is it subconscious?
In our task, it's explicit. We're explicitly telling them to follow through, one way or another to encourage learning. So I think, that for us, it's explicit. I expect people may learn to do follow through implicitly in the sense they find that improves their performance on skills. So we don't know in the real world if people are sensible enough to do that. We know that they're not. We also know that if you just imagine following through, you also can learn separate force fields. Okay, so if you do a movement through a force field and imagine going left or right, you can learn those two force fields. But interestingly, when you actually go to the follow through, there's not so much learning. So it seems like imagined follow through doesn't generalize fully to real follow throughs. But it's clear that when we do our participants in the force fields, they don't use that implicit strategy of imagining a follow through. They haven't learned that. So that's interesting that you can actually, by imagining doing something after a skill, you can improve the skill you do before that, which is interesting to us. It's a novel way you could train in sports, but we don't know whether it would generalize to that sort of field.
Perfect. Since we have a little bit of time, some more on the personal side of things. So lots of early career researchers, PhD students, master students attending the talk. Just was wondering, how have you decided to pivot from medicine into neuroscience? And was that a gradual transition or a sharp transition?
It was quite a sharp transition. I mean, medicine's a wonderful subject to learn. I really enjoyed it, and I practiced for 1 year, the Houseman year, to get registered. But it's somewhat, unlike science, it's somewhat repetitive. I mean, it is a service industry, and you're seeing the same disease over and over again. And I got very interested in neuroscience at that point, and sort of modeling work. And so I decided to go and do a PhD, thinking I might go back to medicine at that point. But I just loved it. And I saw all my colleagues working as GPs and doctors, and it just looked ghastly. I mean, highly remunerative, but it just didn't seem fun to me. So, the beauty of science is you're doing a different thing every day. So I tease my friends, I'm saying, what are you doing Tuesday next year? Oh, you're in clinic. I don't know what I'm doing. So,
right.
But,
sounds like that flexibility and that freedom.
I think the flexibility.
Yeah.
To be honest, and my father is a scientist, or was a scientist, so I saw the flexibility in his life. Not having to go into work till he felt like it. So it does give flexibility.
Fair enough. And do you even today, do you have a thought of how your models can apply to Parkinson's disease patients or CHRM patients, or do you?
Yes, so certainly, so one thing we're really interested in is rehabilitation. So I collaborate with Amy Bastian at Johns Hopkins on that. And one of the problems with rehabilitation is you can bring someone in and get them on a treadmill and get them walking braille, or do something with a robot, and then they go away from the lab, and it just doesn't generalize outside the lab. Okay, so it doesn't generalize from the context of being in the training session to the context of being in the real world. And that's a major problem to rehab. So my hope is, if we can understand context-dependent learning, we can either confuse people so that they don't realize they're in a different context than the lab from the outside world, so it generalizes, or control it in a way so that there's contextual cues which transfer across. So I think, a lot of rehab is great in the lab. It just doesn't actually affect the real lives. And I think that's, we have a grant now to study exactly that. How can we encourage generalization or control context so that people actually express these things in the real world?
Oh, perfect. Are there any other questions from our guests?
I saw one question there which I didn't answer. Someone asking about de novo learning. Maybe can I answer that one? It just vanished. But basically they were asking, don't we reach all the time? So why is this de novo learning? And it's true we reach all the time, but when you reach under a novel force field, a force field you'll experience bar, you have to change your motor commands to account for that force field. So that is de novo learning. You know your arm's properties, but now suddenly there's a new force attacking your arm. If you don't compensate for that force, you don't reach the target. So that's what we mean by de novo learning. And so de novo learning in our heads is really like proper learning. Whereas if you bring someone in and say, oh, use this hammer, they've experienced hammers before, and you're looking at basically recall, or basically what we would think of now as apparent learning as they learn to handle this hammer.
Perfect. Well, I'm afraid that's all we've got time for. Thank you everyone for joining us this afternoon and for all your fantastic questions. Before we say our final goodbyes, don't forget to check out our website on upcoming lectures. The next Turing lecture will be on the 30th of November with Neuroshaker on AI for drug discovery. You can register for these events at turing.ac.uk/events. To be the first to hear about our events, please do subscribe to our mailing list at turing.ac.uk/subscribe. Finally, on behalf of everyone at the Alan Turing Institute, I would like to thank Professor Daniel Wolpert for joining us today It was a pleasure to host you and hear all about your fascinating work. And thank you so much.
Thank you.
Bye-bye.